This presentation will look at the conflicts and trade-off in inherently safer design. Inherently safer design aims to permanently eliminate or reduce hazards with the aim of avoiding or reducing the consequences of incidents. There are four main strategies that can be applied towards achieving this. The first involves minimizing by reducing the amount of hazardous material or energy in the system. The second is to substitute, which involves using a less hazardous reaction chemistry or replacing a hazardous material with less hazardous substitute. The third is to moderate, involving using a material in a less hazardous form or under less severe conditions. The fourth is to simplify, involving eliminating unnecessary complexities to reduce the likelihood of human error. A design can only be described as inherently safer in the context of a particular hazard. The design may or may not be inherently safer with respect to other hazards within the system. Therefore, design must be evaluated separately for each hazard. The application of inherent safety technology, principles, and inherent safer design concepts has been proven to reduce the risk of accidents and is economically attractive for chemical process plants. However, they also suffer from several trade-offs and conflicts that arise from the modifications suggested by the concept. Addressing hazards, it is essential to ask the following questions. First is, can the hazard be eliminated? If not, can the magnitude of the hazard be reduced? Will alternatives increase the magnitude of any other hazards or create new hazards? And at this point, what are the management and technical systems required to manage the hazards which inevitably will remain? Inherent safety characteristics can be determined by the application of safety tools, as can be seen from the diagram below. Example 1 in the next slide shows some common inherent conflicts that arise during process selection and design, and ideas on how to deal with them. In this next example, we see how chlorine gas is substituted with liquid bleach. Liquid bleach is safer to work with compared to chlorine gas. Other alternatives include the use of ultraviolet light and water treatment by generating bleach disinfectant on site. Potential hazards that arise from inherently safer design modifications must be evaluated carefully to avoid misapplication of the inherent safer design strategy. The design decision process must consider the entire life cycle, the full spectrum of hazards and risks, and the potential of transfer of risk from one impacted population to another. Technical and economic feasibility of options must also be considered. As design which is identified to be inherently safer from one hazard could possibly alter the magnitude of other hazards, which were previously not at a critical level, necessitates early evaluation. Any likelihood tool to evaluate the potential hazard conflicts in ISD alternatives at preliminary design stage must cater for potential new hazards and variation of magnitude of existing hazards. In conclusion, can be reduced by many methods, including inherently safer design, but methods must include the full spectrum of risk reduction approaches. This includes passive, active, and procedural risk management systems. This is particularly important in managing multiple hazards and risks. It is unlikely that any single technology will be inherently safer with respect to all hazards. Multiple approaches are required to manage the full range of hazards and risks. Ultimately, society must decide which hazards and risks it wants to manage primarily with inherently safer design approaches and which hazards and risks will be managed in other ways.